Hello everyone, today I'm introducing the Euler's theorem. So first, I'm define phi of a number of n. This means that phi of number n equals to n times 1 minus 1 over p1 times 1 minus 1 over p2 all the way to 1 minus 1 over pn, where n is a number that equals to p1 to some exponent a1 times p2 to some exponent a2 all the way to pn to some exponent an. So this is true because of the theorem of the fundamental theorem of arithmetic. But let's see some examples. First, if n equals to 1000, then the phi of 1000 equals to, because 1000 equals to 2 to the power of 3 times 5 to the power of 3. So the phi of 1000 equals to 1000 times 1 minus 1 over 2 times 1 minus 1 over 5. This equals to 1000 times 1 half times 4 fifths, which equals to 400. So the importance of phi of a number n is because the Euler theorem states that if a and n are relatively prime, then a to the power of phi of the number n is congruent to 1 mod n. So that's the Euler theorem. Another interesting note is that if n is a prime number, then the phi of n equals to p times 1 minus 1 over p1, which is p. So this can be simplified as p minus 1. So a to the phi of n is congruent to 1 mod n is thus equals to a to the p minus 1 is congruent to 1 mod p. And this is just the Fermat's-Little theorem. So there are interconnections between Euler's theorem and Fermat's-Little theorem. Now let's look at some questions. The first one is to determine the last two digits of numbers. And the first question is 117 to the power of 82. So in order to determine the last two digits, we must find the number modulo 100. However, we learned from the Fermat's-Little theorem that if 117 and 100 are relative prime, then 117 to the power of 99 is congruent to 1 mod 100. But we cannot use this one to find 117 to the power of 82, which is less than 99. But from Euler's theorem, we have phi of 100 equals to 40. Then 117 to the power of 40 is congruent to 1 mod 100. So for the 40 part, we have 100 equals to 2 squared times 5 squared. And phi of 100 equals to 100 times 1 minus 1 over 2 times 1 minus 1 over 5, which equals to 40. So we have power of 2 on both sides, then 117 to the power of 80 is congruent to 1 mod 100. And we times 117 squared on both sides. Then you can find that 117 to the power of 82 is congruent to 117 to the power of 2 we know that we are finding the last two digits, so this is, we can actually use the 17 squared because the last two digits are only related to 17. So 17 squared is equals to 289 mod 100. And 289 is congruent to 89 mod 100. Thus, we solve the question that 117 to the power of 82 is congruent to 89 mod 100. 89 is the last two digits. For the next one, 2 to the power of 777. We are finding the last two digits of this number, so we are using mod 100. But the Euler theorem said that if the greatest common divisor of a and n equals to 1, then we can use the Euler theorem. But GCD of 2 and 100 does not equals to 1, it equals to 2, so we cannot use the Euler theorem on 100. But 100 is also equals to 4 times 24, 4 times 25. And 4, we know that 4 divides 2 to 777, then we can only find 2 to the power of 777 mod 25. Now, we can use the Euler theorem because GCD of 2 and 25 equals to 1. Thus, phi of 25 equals to 25 times 1 minus 1 over 5, which equals to 20. Thus, from the Euler theorem, we know that 2 to the 20 is congruent to 1 mod 25. And 2 to the 777 is equals to 2 to the power of 20 to the power of 38, which is 760. And we times 2 to the 17 on both sides. Thus, 2 to the 777 is congruent to 2 to the 17 mod 25. For mod 25, we have 2 to the 7 equals to 128, which is congruent to 3 mod 25. Thus, we can simplify 2 to the 17 as is congruent to 2 to the 7th times 2 to the 7th times 2 to the power of 3, which is congruent to 3 times 3 times 8 mod 25. And that's 72. So 277, 2 to the power of 777 is congruent to 72 mod 25. And 72 is congruent to 22 mod 25. And last but not least, we have 2 to the 777 is congruent to 22 mod 25. But does that mean that the last two digits of numbers of this number is 22? We notice that we are finding the number of mod 100, so thus the left side must be divisible by 4 and the right side must be divisible by 4. However, 22 does not divisible by 4. But for the multiples of 25, we have the numbers that end with digits 0, 25, 50, and 75. If we add 22 on each of them, we have 22, 47, 72, and 97. This one is the only number that is divisible by 4. So the last two digits of 2 to the 777 is 72. For the next one, determine the last 3 digits of 351 to the power of 412. And it's an easy question because we are determining the last 3 digits, which is mod. We are finding mod 1000, and we know that phi of 1000 equals to 400, as we determined that previously. So 351 to the power of 402 is congruent to 351 to the power of 400 times 351 squared, which is congruent to 1 times 351 squared. And while we find the last 3 digits, the only thing matter is 51 squared. So this is congruent to 51 squared, and 51 squared is 601, and the last 3 digit is 601. So this is congruent to 601 mod 1000, and we solve the question. We determine the last 3 digits is 601. Now let's look at the last question. Let a be a positive integer with GCD of a and 10 equals to 1 shows that the last 3 digits of a to the power of 101 is the same as a. So first, while we find the last 3 digits, we are using the mod 1000, but phi of 1000 equals to 400, and we cannot apply this 400 into a to the power of 101 because 101 is too small. But for 1000, we can split 1000 into 125 and 8, and we find each individually. So first, the phi of 125 equals to 125 times 1 minus 1 over 5, which equals to 100. Thus, we have a to the 100 is congruent to 1 mod 125. Thus, a to the 101 is congruent to a mod 125. Now let's look at 8. So we have phi of 8 equals to 8 times 1 minus 1 over 2, which equals to 4. So we have a to the 4 is congruent to 1 mod 8. So a to the 100 is congruent to 1 mod 8, and it follows that a to the 101 is congruent to a mod 8. Thus, a to the power of 101 minus 8 is divisible by 125 and 8, which is 1000. Thus, we prove that a to the power of 101 is congruent to a mod 1000. So this gets a conclusion that the last 3 digits of a to the power of 101 is the same as a. So a tricky part of this question is that you can ask your friend what is the last 3 digits of 256879 to the power of 101, and you can get the answer, which is 879 immediately. So that's useful conclusion. So if you have any question, please contact my email. See you next time.